In this video, we're going to go through the tension design of structural steel members based upon the New Zealand design standard NZS 3404. So previously we've looked at where we're going to see tension members in buildings and other structures, and just generally how some of the failure modes look like. But in this video, we're going to run through what some of the actual design equations and a bit of the processes are. As really just an introduction. And so, as I said, let's just jump into it. The governing equation that we're going to look at is going to be similar to most of the equations we're going to look at with steel design, where we've got some load. In this case, it's going to be called N star, and that load has to be less than our capacity, which is our strength reduction factor phi, times our nominal tensile strength. And so, this is, just very similar to what we'll see as a pattern for whether we're looking at tension or compression or bending or shear. All of these are going to have this form. And I've, in sort of brackets here, I've highlighted where the different sections where you can find these equations in the steel standard. So that's all pretty straightforward. Now, one thing to note for the strength reduction factor for steel sections, that's going to be 0.9. It doesn't matter whether you're looking at tension or compression or shear. For the way that the New Zealand design standard takes it up is that phi factor is going to be 0.9. Now let's look at just a few more aspects of this. So the factored load is pretty straightforward. This would be coming from your analysis and the demands on the structure. But let's look at this factor ends of t. So what our nominal section capacity is. And the way we define that is we're looking at really two different failure modes. And so the failure modes that we're interested in are going to be either yielding of the gross section or rupture of the net section. And it's going to be the smaller of these two. It governs the design. So if that's the case, well, we really need to figure out, how do we calculate these two sections and the two section capacities of either yielding over the gross section or rupture over the net section. So what I want to start with is actually just looking at, this yielding of the gross section. And we'll start by just sort of throwing out what the equation is, and then we can sort of walk through graphically what it all means. And so the equation for yielding of the gross section, our section capacity N of T, is going to equal the gross area of the section times Fy, where Fy is the yield strength. So the yield stress of the steel, and Ag is the gross area of the section. And in fact, we'll just go ahead and box in that equation. So what do we mean? So the yield stress of the steel is pretty easy. We can look that up. What do we mean when we're talking about the gross area of the section? Well, if we draw a little member here that's in tension, and we give it some thickness, well, say it has width B and thickness T, and we'll put it under tension here. Well, pretty straightforward, just the gross area. It's just going to be just the area of that section which is in tension. So it's just going to be the width B times the thickness T equals gross. area. So that's pretty straightforward. And then, of course, our Fy for steel in New Zealand is going to depend on both the grade of the material as well as its thickness. Because recall that with steels in New Zealand, thinner steels have a higher yield stress for a given grade. So grade 300 steel has a nominal yield stress of 300 megapascals, but any plate which is less than 11 millimeters will have a yield stress of 320 MPa due to the finer grain structure. So it's just a small thing to have to keep in mind. So that's yielding of the gross section. So now we know how to calculate one of our two, section capacities, nominal section capacities for an element in tension. The next one which we have to look at is rupture of the net area. So we'll just go ahead and write that down. All right, and so again, with net area, think about you're going to, as different from the gross area, it's going to be a portion of your section is missing. And if you want another mnemonic to try to keep this in mind, and think about it, a net has holes. So if you've got your net here, of course it's got holes in it. Our net section is going to have holes in it, and just for fun, net's there to try to catch those fish. All right, so enough of that. Let's look at a more sort of specific example for steel. So again, we're going to go ahead and draw ourselves a section here. But this time, our element has a portion missing. It's got some holes in it. And again, we'll put this guy in tension. So just like we did with our yielding of the gross section when we wrote that down, let's go ahead and just write down the equation, and then we can look at each of the parts and what do they mean physically and why are they there. So our nominal section capacity for when we're looking at rupture of the net area, ends of T, is going to equal 0.85 times K T of E times AN times the ultimate tensile strength. So AN is just simply the net area. FU is the ultimate stress of the steel. This KTE factor is what's called a joint efficiency factor, or it's a reduction factor for joint efficiency. And with this, for plates and elements which are sort of connected symmetrically, it's going to be 1.0. We'll just have a quick look at what this is just in the standard. So it's in table 7.3.1, and we'll look at this in more detail when we come to shear lag. But as you can see, it's going to range from 1.0 to 0.75, depending upon the configuration of your element. But for now, we're just going to sort of park that. And then finally, uh, 0.85 is a factor to ensure that local brittleness isn't going to cause premature rupture. And so, yeah, that's in a nutshell what all of our different factors are. Much like when we had the yielding of the gross area, I think what would be worthwhile is just spending a little bit of time looking at this net area calculation and how we would go about that. So just go over to another page, and we would say for calculating the net area. Alright, so in doing that, really what we want, I'll draw the picture first, and then we can have a look at how we would go about actually calculating it. It's a fairly straightforward calculation, but it is always worthwhile to just have a visual to keep in your head, so that when you go through these calculations, you're not trying to memorize different equations, but in fact you're just sort of stopping and thinking about, well, what are the demands on the structure, and how does that relate to the capacities I'm trying to calculate. So say we have this element here, and it's in tension, and it has two holes. So we already looked at how to define the gross area. Now the net area is going to be, as I said, net area is when we have a portion missing. So what we're looking at are lines of failure. And so for here, we'd be looking at sort of this first bolt as a line of failure. And if I take that and I sort of draw it over here, just a bit bigger, what we've done is we've sliced right through the middle of that hole. And the reason that we've done that is just simply that the net area is going to equal the gross area minus the area of any holes. As I said, pretty straightforward. And we want to go where it's going to be the smallest section. So we've got the smallest area because, if you recall, whatever is going to be the smallest nominal capacity is what's going to govern our design. So we're looking for the smallest net area here. And to do a little bit of shading. All right. And so what we want to do is figure out, well, how big is the hole? And how do we account for that in our design? So what we're going to do is, in fact, use what's called a projected area. So if I sort of project out where the hole is, it's going to be this sort of hatched area here, which has a thickness of t and a width, the diameter of the hole. And so now it's quite straightforward. We can take the gross area, which is going to be, the total width of this element minus the diameter of the hole, and we'll multiply all of that by the thickness. And that should make some sense intuitively with this projected area. All we're really doing is looking at where the largest section of the hole is going to be. That's going to be the diameter. And then we can sort of pull out from there what our area of our holes are and what that net area is. So this is going to be the projected area of the hole, and the area of the hole equals the diameter of the hole times the thickness of the plate. And if we've got more than one hole in a line, well, it's just, times the number of holes. Or if we've got different size holes, we can account for that in the same manner. And now, one of the last questions on this is, how big is the hole? And for, because most of what we're going to look at are going to be bolted connections, we'll just have our little rule for that. So for bolted connections, what we want to do is take, so for the diameter of the hole, because what we can't do is we're not able to just have a hole which is the same diameter as the bolt. It won't fit. We need some additional size to allow us to be able to physically put together the structure with this bolts. And so what we know as a minimum that we need the bolt diameter plus we need 1 millimeter for clearance. And that clearance is just to allow the bolt to enter the hole. And then we also need 1 millimeter for tolerance. And that tolerance is going to be in case, during fabrication, the bolt hole wasn't perfectly centered. It gives some ability for to not have a perfect perfect manufacture. And so that's really our bolt holes are just going to be the diameter of the hole equals the bolt diameter plus 2 millimeters. So that's a pretty easy rule. And then as you go through and you do these designs, you'll pretty much just sort of intuitively you'll memorize that one. That's like, okay, if I'm using an M24 bolt, it's 24 millimeters in diameter, I need 26 millimeter diameter holes. So with that, let's just do a quick example to wrap up this video, just sort of bringing this stuff together. And so the design example I have here is a fairly simple connection, so it's going to be welded on one side. We're going to ignore that here, and we're going to look at just really this end where we've got 2 bolt holes. I'm saying that we're using M16 bolts. We're using grade 300 plate that's 10 millimeters thick, so this is the material property, so yield stress of 320 MPa and an ultimate stress of 430 MPa. And I'm just going to give you the fact that KTE is going to equal 1. And what we want to know is the maximum tension that the element can carry. All right, so in doing that, really what we need to know is we find out, of course, our governing equation is n star is less than or equal to phi n's of t. We know that phi equals 0.9. We need to find n of t for our 2 different sort of governing cases. That's going to be the first one of which is going to be the yield of the gross section. And so our gross section, if we look at our example here, that gross section is going to be anywhere along here. So we'll say this is going to be a gross, and we'll just draw our little picture here just to be clear on what we're calculating, just because this is the first time that we've done it. And of course we're going to have a distance of 100 millimeters wide and 10 millimeters thick, and that's going to be a gross. So ends of t equals ag times fy. That's going to be 100 millimeters wide, so 30 plus 30 plus 40, times 10 millimeters times 320 MPa. And then we need to divide by 1,000 newtons per kilonewtons, because with structural engineering, we tend to work in kilonewtons and not newtons, just given the size of the demands we have. And so ends of t equals 320 kilonewtons, and phi ends of t equals 0.9 times 320 kilonewtons. Phi ends of t equals 288 kilonewtons. All right, so that's our first sort of design case, or which might govern, and the other one we have to look at is the rupture of the net area, the net section. Now with this net section, again, this is where we have the holes, and so the line where it would fail would be right through here, so that's AN, and I'll go ahead and just draw a little picture of what we have that we're actually trying to calculate an area for. Now, because we've cut right halfway in between, right down the middle of the hole there, that section, which we're essentially designing our net area for, looks a bit like this. And where our net area is just going to be this shaded part. And of course, that's going to be the same as our gross area minus the holes. So just move this up so you can see it. And of course, that's going to be, we'll just do a equals AN. So our section capacity for a net section is going to be AN times KTE times the ultimate stress times 0.85. So AN is just going to be our gross area minus the area of the holes, and that's going to be 100 millimeters times 10 millimeters times 2 holes times 16 plus 2 millimeters. And 16 plus 2 because we have M16 bolts, but we need that 2 millimeters for the clearance and the tolerance. And so that gives us a net area equal to 1,000 minus 360 AN equals 640 millimeters squared. We need to just go ahead and plug that into this equation. So we get 640 millimeters squared times 1.0. Again, this was given to you. It's also going to be 1.0 because it's a flat plate, which we will discuss later, times 430 megapascals for our ultimate MPa times 0.85 over 1,000. And then if we crunch those numbers, we get 0.85. We get Ns of T equals 168 kilonewtons. Phi Ns of T equals 0.9 times 168. Phi Ns of T equals 151 kilonewtons. And then looking at these two, well, 151 is definitely smaller than 288, and so it's going to be the rupture of the net area governs the design. So that was just a really quick design example. It should be pretty straightforward, hopefully, for when we're just using these flat plates. We're going to look at some slightly more complex scenarios, for when, example, KTE does not equal 1, and when we have things such as block shear, which we have to account for. But overall, that is the main sort of methodology for how we do tension design. So with that, thanks for watching.